Hi everyone, I'm Tanvir. I work with Dr. Tanvir Hossain. So today's topic that I will describe here is HOACS, that the framework we have developed for protecting data. But you can see the name of the presentation or the name of our journal. So it's too much, like it's too big and it's too complicated to understand right now. So let's ignore it for now. So we put that title because of the journal. We have to give fancy title and everything. That's why. So I made this presentation just to give just some idea of the research. There will be no complex math algorithm or anything complex. I just made it to give the idea so that general audience can understand. I think we have people from computer science, electrical engineering, data system, or different fields. So if I talk about more algorithm and math, it's gonna be too much. That's why I tried to make it more simple, and you'll not see too much math here. So first, think about some cool thing, that software hacking. We all know about software hacking, and you can find a lot of examples, news, everything in the internet about software hacking. But there's another kind of hacking that can happen to your iPhone. Suppose we have apps and everything in the iOS, everything that can be hacked, that is called software hacking. But another thing can happen in your phone, in your system, in your server. What would be that? Can anyone answer it? Yeah, hardware hacking. Hardware hacking is real, and people do it. If there's examples, this is the most like popular example of hardware hacking, the big hack. So what Amazon did, they ordered some equipments from another vendor called Supermicro from other company. They installed this equipment in the server of government agencies and their AWS facilities. And then they found out that some data got leaked. And then when they investigated and saw when they reassembled that part, you can see here, when they reassembled it, they found something interesting, just a tiny little dot here. And they found out that this tiny little equipment is constantly leaking data from their server. So this is actually hardware hacking. The attacker installed something malicious inside the hardware, and that is leaking your sensitive data. So keep in mind, when a hardware is manufactured, you cannot reverse it. In like reversing hardware is not feasible in systems. So we'll talk about it. So why this happened? So this is the global chip manufacturing supply chain, or the how much percentage the countries have. So you can see the supply chain is diverse. People from all over the world, either they're manufacturing, they're assembling, they're testing. So the supply chain is diverse all over the world. And if you think about from US perspective, US only manufactures 7% of the chip or the electronic components. Other than that, other offshore countries, they manufacture all those equipment. And that creates the threat of piracy, intellectual property theft, overproduction, and the Trojan insertion that we actually saw before, that they inserted something malicious inside the hardware. So this is the block diagram or academic block diagram of the supply chain. You can see if a design house wants to make a chip, they will send the design to the SoC integration. After that, that company will send the design to the foundry. Foundry will manufacture that die, and they will assemble it. They will test it in the different companies. So all the companies are different, and that these companies can be in different countries like China, Vietnam, Korea, India, or other countries. So now in current scenario, we are working on the total trust. All the company that working on chip, they assuming that the company, all other companies are trustable, and they will not do anything malicious with the chip. But recently, there was a term, Department of State, they actually introduced something called zero trust. It happened after the incident of Edward Snowden in NSA. He leaked some data from there, and then all the government agencies thought that, okay, insider can be a threat. Insider person or insider entity or any kind of protocol in the network can be a threat to the system. So they introduced something called zero trust. That means from your perspective, you see every other companies or entities as a threat, and you will design your system like the way so that they cannot do anything malicious with the uh, system. So here is an example of the zero trust. Suppose you're developing something from here in USA, and you're sending some data or your IP to the other countries. You will consider all of them as a threat, all of them uh, like as a threat, and we call it a zero trust. So that means that we will not trust anyone. We'll verify it, and then we'll trust. That is the motto of the zero trust. So with the zero trust, all this protection that happen in the total trust will not be effective. And what can be an example of zero trust? That is COTS processor. That means commercially off-the-shelf components that we buy any kind of components from the market that we install it in our server system. Suppose this guy is Ashraf, our IT manager. He went to, we need some chip for the ITTC server, and he went to some market like Best Buy or Target. He got some chip from there, and then with his respective team, he installed that chip inside the ITTC server. And then think about it. Can you trust this chip in your server? No, right? And you can say, okay, Ashraf is doing it. ITTC don't deal with too much sensitive data, but the research, this report of DoD, they have shown that almost 72% of the government agencies, they are using commercially off-the-shelf components in their server systems and facilities. So this is a major threat, right? So the chip he got from the Best Buy or Target or any other vendors, third-party vendors, he doesn't have the blueprint, any reference if these chips are like malicious or not, right? So here is the problem. Suppose if you go inside the chip and if it is malicious, what you'll see? You'll see that those architecture change, and if attacker wants to leak something from that, suppose they will put some malicious circuit. So every time you are updating your register inside the chip, the data will get leaked and attacker will get your sensitive data, right? So this is a real problem. And as we all know from the beginning that once hardware is manufactured, you cannot change it. You cannot modify your hardware. So how would you deal with the malicious or untrusted hardware in your system? Can anyone answer? Probably a software-based solution. Okay, that's why we adopted this number coding system, that is residue number coding, or you can say residue number system, that actually diversify your data in different parts so that when you are executing some operation, the register file will not get the real data. It will get the encoded data. And when the operation is done, and then you will decode it again. So basically what we are doing with RNC, we are just diversifying the data, and then we are performing the operation, and then we are decoding. So even if the attacker gets the data, they will get the encoded data, right? So our system will be protected. Our sensitive data will be protected. Here is an example of, I promised you there will be no math, but here is an example, just a simple example of RNC, how RNC works. Suppose we have two numbers, 29 and 27, and you want to like perform an operation, arithmetic operation, that is addition. In general, what we'll do, we'll just add 29 and 27 and we'll get 56, right? This is the normal way of operation. But in RNC or residue number system, we'll have those modules. User can pick those modules. You can set the number of modules. Here we are using 2. You can add like 100 modules or 1,000 modules. That will secure your system more. So what we are doing, we are just getting the modulus of those number, and then we are performing on those diverse data. And then when the operation is done, and then we are going back to the original number with Chinese remainder theorem. These are complex math. We have them on our paper, but I didn't include it because of like for the general audience, because it will be boring. So yeah, so we got our solution, right? Problem was we have to protect the sensitive data. Now we got the solution of residue number. So here comes the homomorphic encryption part. If you are doing any kind of operation on encoded data, and that is kind of like homomorphic encryption, and then that is a simple example of homomorphic operation. That is, you will encrypt the data, you will do the operation with the encrypted data, and then you will decrypt it again. So basically, our framework is like this. And what is the proposed framework? First, we'll initialize the program that we want to convert with RNC. And then we'll encode the secret asset. That means secret data, some data, not the whole program. Because if you encode whole program, it will be so like a resource consumed, and overhead will be higher. So we'll just encode the secret asset, and then we'll do the execution in the secure program, like execution, and then we'll do the decode operation. And then secure operation will be terminated. This is the simple form of our framework. And the framework can provide different common type of arithmetic operations that we need to perform, or like regular programs, that is addition, multiplication, like equal or exponential terms. So now we have the framework, we have to test it in some place, or we have to test that our protection is working, right? So here's the experimental setup. First, we got a program. It's an example program. You don't have to take the AES. You can take your own program. We got the baseline AES that is unprotected. The HOACS framework that we are proposing, it will go through that. We'll convert that to the RNC system. That will be HOACS protected AES. That is secured. We are telling it. And then we will compile it. We use Gem5 x86 architecture to simulate the program. And then we match the output. We match that if the baseline AES and protected AES output is same or not. And then we got the register trace. Our goal was to protect the sensitive data to be leaked by the register files, right? So we got the register traces using Gem5. We built the key finder tool. That means that tool is basically searching the AES key inside the register. Like we are trying to protect the AES key, and we analyze the data. This is the experimental setup of our framework. And then when we analyze the key or the register traces, you can see when we are doing the encoded execution, with baseline AES, we have the traces here, but in the middle. So what is this 0, 1, 2, 3 means? This 0, 1, 2, 3 means we just divided the whole program in 4 parts, and these 2 parts, 1 and 2, these are the encoded execution. 0 is the initialization, This is the termination of the program. So our goal was to protect the secret key in this part, right? So when encrypted execution is happening, we saw that okay, the raw key of AES is not exposed in the registers. But when the baseline AES is running, raw key is exposed in the registers. And then, so we got the result that, okay, it's working. Now overhead, unlike other homomorphic encryption framework, our framework is giving lower overhead. And this is because we are not dealing with lattice or ring-based encryption that people use in homomorphic. We're just diversifying the data using RNC. That's why our overhead is much lower than the other existing framework. In summary, okay, what was our question, research question? We wanted something that is robust, we can execute the code securely inside the untrusted hardware, right? And our proposed solution, the RNC framework, and that can encode data, execute it in the processors, and then you can get the decoded data. And what was the experimental setup? We made a C language-based framework, ran it on x86 architecture, and showed that, okay, our framework is protecting the data, and we got the lower overhead and everything. I guess, like now we all understand what we have done so far. Now, probably if you go back to that slide, now it will make more sense, like what is homomorphic obfuscation, assisted concealing of the secret to Thwart, Trojan attack in COTS processor. Basically, we are using homomorphic obfuscation technique in COTS processor to protect the data from hardware Trojan attacks. That's the simplest form of this research. And that's all. Thank you.